Welcome to this explainer. We're jumping right into a really mesmerizing 3D geometric journey today. We're going to take a concept that, well, you probably remember from high school calculus, tear it right down to its visual core, and watch it spiral into literally one of the most beautiful and chaotic structures in all of mathematics. We're talking about mathematical analysis, specifically the geometry of Newton fractals. Let's get right into it.
So, how do we actually predict an asteroid impact? I know, it sounds like the setup for a massive sci-fi blockbuster, right? But fundamentally, it's a problem of measurement sensitivity. It's all about extreme precision. To know exactly where an object flying through space at thousands of miles an hour is going to be at any given millisecond, scientists have to solve incredibly complex equations. Or more specifically, they need to find what we call the roots of these equations, those exact precise points where a function crosses zero. And to pull this off with life-saving accuracy, we actually rely on a brilliant, centuries-old geometric engine.
Picture this, a dynamic 3D coordinate plane right in front of you. Right in the center, there's this smooth, glowing blue parabolic curve representing our function. Now, our ultimate goal is to find exactly where that blue curve slices through the horizontal x-axis. But we don't just guess blindly, right? Instead, we pick a starting point somewhere on the curve. From that spot, we draw a striking red tangent line that perfectly grazes the curve, and we just follow it, sliding straight down until it hits the x-axis. And that intersection point right there, that becomes our geometric homing beacon. Let's see how this geometry builds into an automated algorithm. It's honestly a beautiful loop. Step 1, we pick an initial guess. Step 2, we draw that red tangent line straight down to the x-axis. Step 3, that new x-intercept becomes our brand new guess. And then step 4, we repeat the whole process over and over. With every single loop, we generate a new red tangent that just continuously closes in on the true root. It's like watching a mechanical process zeroing in on a target with absolute laser precision. The geometry is literally doing the heavy lifting for us here, guiding us step by step to the exact answer. Now, this whole visual dance translates perfectly into math. Newton's method formula. It looks a little intimidating on the surface, doesn't it? xn plus 1 equals xn minus f of xn over f prime of xn. But honestly, it's just the algebraic translation of the exact geometry we just saw. The new guess, xn plus 1, is found by taking our current guess, xn, and subtracting the height of the function divided by its derivative, f prime of xn. And that derivative? It's just the mathematical way of writing the slope of our red tangent line. The algebra and the geometry, they perfectly mirror each other. And this right here illustrates exactly why this method is so famous. Its sheer, breathtaking speed. We call this super quadratic convergence. Once that red tangent line gets reasonably close to the true root, the method acts like a gravitational tractor beam. With every single step, the number of accurate digits in your answer roughly doubles. 2 accurate decimal places suddenly become 4. 4 jump to 8. 8 explode to 16. It is a supercharged geometric engine that finds the truth way faster than almost any other basic algorithm out there. But, of course, there's always a catch. Let's move into our next section, the glitch in the matrix, where we look at method failures. Because, math is rarely without its drama. What happens when this seemingly perfect geometric engine just stalls out? As powerful as Newton's method is, it has some pretty fatal blind spots. Think back to our red tangent line for a second. What if we make a guess at the exact bottom of a curve, where the slope is perfectly flat? Well, the derivative is 0, so that red tangent line becomes perfectly horizontal. It's just going to run parallel to the x-axis forever, never actually intersecting it. The algorithm instantly crashes because you're trying to divide by 0. Other times, a bad initial guess can cause the red line to just bounce back and forth between 2 points in this endless, infinite oscillation. Or worse, it shoots off into an entirely invalid domain, millions of miles away from our actual target root. To really put this into perspective, let's contrast our ideal scenario, that super-fast quadratic convergence, with infinite divergence. Our sources highlight this incredibly fascinating example using the function tangent x equals 0. The true root there is exactly 0. Now, if you start your guess at 1.08, the method easily finds the root in just 6 steps. Boom, done. But if you shift your guess by a microscopic fraction, just bump it to 1.09, the tangent line's wildly overcorrect. By the 7th iteration, your guess is negative 126 billion. There's no way around it. The algorithm utterly loses its mind and just diverges into absolute chaos. Which brings us perfectly to our next section, entering the complex plane and the basins of attraction.
This fragile little balance between rapid convergence and wild divergence really opens the door to our next frontier. We're leaving simple 2D curves behind and stepping straight into the complex plane. Take a look at a cubic function, like x cubed minus x. This one actually has three different roots, -1, 0, and 1. Because there are multiple targets now, our geometric engine has a choice to make, right? So we color code the starting points based on where they eventually land. We call these basins of attraction. If you drop a guess anywhere in the blue region, the tangent lines will always guide it to the root at -1. Start in the bright red region, it gets pulled to 0. The vibrant green region pulls to 1. In one dimension, it kind of just looks like a simple, color-coded ruler. But just wait until we expand this.
Because now we arrive at the main event. Newton fractals, the geometry of chaos.
Okay, what happens when we map these colorful basins of attraction across a massive, sweeping 2D grid of complex numbers? On the macro view, you see these vast, solid continents of red, blue, and green. But watch closely what happens when we zoom in on the borders between these colors. Do you notice something mind-bending here? The colors never smoothly transition. Never. Whenever a bright red zone and a deep blue zone try to touch, a brand new, microscopic patch of green suddenly bursts in between them to keep them apart. And if you zoom in on the edge of that green patch, a new red and blue structure appears. It repeats infinitely, creating a fractal. It is this visually mesmerizing, infinitely complex tapestry that is generated simply by repeating our geometric tangent line over and over and over again.
And this brilliantly illustrates an absolutely crucial tenet of chaos theory: extreme sensitivity to initial conditions. Right along those complex fractal boundaries, you could have two initial guesses that are practically touching, literally separated by a billionth of a decimal point. Yet, because of the infinite complexity of the fractal border, one guess will confidently slide down the tangent lines straight into the blue root, while the other will spiral wildly off into the green root. The absolute slightest flutter, just a microscopic shift, wildly alters the final destiny of the calculation. So, what does this all mean for us? A simple tangent line equation births infinite, chaotic complexity. I mean, think about it. We started with a very practical real-world challenge, right? Drawing a simple straight line to find a root so we can do something like predict the precise trajectory of an asteroid. But by pushing that basic geometric tool to its absolute limits and feeding it into the complex plane, we stumbled right into breathtaking, unpredictable chaos. It just goes to show that in mathematics, the most rigidly structured rules can effortlessly give rise to the most beautifully infinite mysteries. Thank you so much for joining me on this explainer. I hope it sparked a whole new way of visualizing the math all around us.